20315.
لا 23015.
23015, okay, 015. And I will go to any airfoil library, just like this one in here. And this is your airfoil. And what you see down here, do you see that on screen?
يا هذه فتحناها الموقع ذا امس.
Okay, so you have these, you see these values x and y, x and y, x and y. It's the coordinates of all these points, right?
اوكي لا انا ما كنت اعرف المعلومه هذه.
دي coordinates. You see, let's read the first point. 1 at 0.0016, it's that point. Okay, then 0.95 and 0.012, it will be here. That's the second point, the third point. So if all these points are x and y of all the points of the airfoil. Now let's say you decided to put the fuel tank between this line here, here, and here. So all you have to do is to find the distance from here to here, and the distance from here to here. That's the 8% that you had. So the 8% that you had would be slightly smaller than this. Not 8%, I'm sorry, the 8 inches or whatever. Now, how do I know this height? In the airfoil X and Y here, it's based that the chord is 1. So for example, this height here might be 0.15. It's 0.15 because the chord is 1. How do I get the height? It's the difference between this point and that point, or you draw it to scale. Okay. So if this is 0.15, then the fuel tank maybe will be 0.12, slightly smaller than the 0.15. And please remember that this is based on a chord of 1. All the chords on the internet have a value of 1. So if your chord is 4, I will take the 0.15 or 0.12 and I will multiply it by 4. So it will be 0.48 feet. Now you see how we calculate it.
إيه تمام. بس دكتور عندي كمان سؤال ثاني. مثلا امس يعني بما انه يعني قلنا بنسالك بس قلنا نجرب كم شيء. حطينا كم قيمه ويعني اتس انسايد رينج وطلع معانا صح الفوليوم حق التانك. ينفع كذا ولا؟
ما هو لازم يطلع. ما هو يعني ايه طلع معانا؟ ما هو اكيد هيطلع الفوليوم حق التانك لاني ببساطه ممكن تغير الطول. قول لي بقى الدايمنشنز كام هنا؟ يعني انت يو اسيومد الهايت صح؟
ايوه صح.
كويس. وحسبت الطول ده وحسبت الطول ده تمام؟
ايه.
طلع الطول ده كام اللي يديك الفوليوم؟ هو ده السؤال. اللينث ده طلع كام؟ ما هو لازم هيطلع طول، لكن تفرق لو طلع 3 فيت عن طلع 4 فيت عن 10 فيت. طلع كام؟
يعني ما ينفع بس انه نحط الارقام وتطلع
ما هو ما
مثلا.
ينفعش. اصل انت بتقول لي I can get the dimensions of a fuel tank that will fit that volume صح؟ This is what you did.
Yes.
I can always have a solution for this. I can always find a dimensions that will fit a certain volume. السؤال are they okay or not? Because for example, if this wing, you see this wing, 17.64 span. If you tell me the fuel tank is 10, that means the fuel tank will go all the way to here. That's not acceptable.
اي صح اكيد.
Okay, so you have to, you got the numbers? Tell me the numbers. Do you have this length?
عند نواف.
Okay, send me later and we can check that. Okay.
تمام.
Or you can judge it. If the length is more than 1/3 half span.
لا طلع رقم صغير. طلع رقم صغير
ما
ابدا.
مرة أقل.
And it's okay. If there is no numerical mistake, send it to me and I will check.
Okay.
Okay. So I hope this was good for everyone. Now let's any other questions from other teams, because basically we will be answering your questions today and Monday. Okay, let me share you this file. Now you can see the new slides, better weight estimate.
ايوه دكتور.
Okay.
Yes, doctor.
Okay. So if you have no other questions, we will go with the better weight estimate. So what we did, we finished last time the configuration. We had a drawing of an aircraft, a complete drawing on aircraft. So today we are going to see how heavy this aircraft is. Now, you might argue, but we already did that. We looked at the range, remember the range, and we calculated the weight ratios and we got the weight estimates. That's okay. That's what we did before. And it was like 5,000 something. That was the total weight based on that range and fuel and stuff. But you see, what we have today is this. We didn't have this when we estimated the weight 4 weeks ago or 3 weeks ago. Now we have a whole lot of information. Who guarantees that the weight of this design is the same as what we found from the weight of fuel? So, okay, okay on the video recording. So the way to do this is that we rely on experience, and by experience, people can look at the aircraft and just guess it's about 4,000, 5,000, and so on. But that's not a very good way. Better way, if we know the weight of the different components of the aircraft, I can add these components and see if I will get the same weight that I had before. We call this the weight buildup method. So for the weight buildup method, I will estimate the weight of the wing, the fuselage, the tail, horizontal and vertical, the landing gear, all the smaller components, and I will add them and see if the weight is the 5,000 something that we had before. For this, we will rely on the experience of previous designs. What does that mean? People have long known that if you know the external surface area of the wing, which is called the exposed wing, all you have to do is to multiply it by 2.5 to give you a reasonable estimate of the wing weight. And we did that before in the wing, by the way, a couple of weeks back. If I know the exposed area of the wing, which is the area of the wing outside the fuselage, not counting the part that will go inside the fuselage, only this part. If I know this chord, this distance, which we all have now because we have drawn, this area is called the exposed surface area. If it is 100 square feet, then the weight of the wing is about 250 pounds, roughly, because that's the typical weight of an aluminum wing of that area. The same goes for the horizontal tail. If I know the exposed area of the tail, which is this area in here, if I have the area, and we have it because I have the drawing with dimensions, multiplied by 2. And you realize that the factor is different because typically horizontal tails are thinner than wings. The same for the vertical tail. So these three are easy, and now comes some tricky parts. Can you estimate the fuel? Yes. Question? Okay. So you can estimate the fuselage weight by multiplying the external surface area of the fuselage, which is called the wetted area, by 1.4. Now that's a tricky part. Can you estimate the external surface area of this fuselage so that I can multiply it by 1.4 and get an estimate of the weight? Remember, I have all the dimensions of the fuselage. I know this length, I know the width, I know the height. I know all the dimensions. Can you estimate the weight, the external surface area of this fuselage? Now, people have done so in so many ways. Earlier, what they do is that they can make a model made of wood, for example, and they will cover that wood, that fuselage. They will cover it sometimes with graph paper, ورق رسم بياني, and they simply counted the number of squares. That will tell them the external surface area. Very rough, but very simple way to get the external surface area. Others would coat the model, maybe with cadmium or nickel, just like you coat jewelry and stuff, and they calculate the amount of coating, and that will tell them the external surface area. Now, these days, the easiest way, of course, is to draw the aircraft on SolidWorks, any 3D modeling tool. So draw it on SolidWorks, and he will give you directly the external surface area. But if I don't know how to draw it in SolidWorks, or if I'm in a quiz or I'm doing a homework and I'm not going to draw the whole aircraft just to get the area, there are other ways to estimate the external surface area. For example, you might want to you might want to divide the fuselage into a cylinder, maybe a smaller cylinder, and a cone. And if I calculate their external surface areas, that would be a reasonable estimate. So basically, that's the way we are going to do it for the wet surface area of the fuselage. The passenger cabin is a cylinder. The nose is another smaller cylinder. And this is the tail cone that we have here. If I have the length of each part of them, if I know the diameter of each one of them, then I can get the external surface area. Pi times the diameter times L is the area of section A. Pi times the diameter times L is the area of section B. And 1/2 pi times diameter times the height is the area of section C. Add them and you have an estimate of the surface area of the fuselage. Any questions here? Now, this is not always the case. Maybe in a military aircraft, the nose is not a cylinder, maybe it's another cone. So in that case, it will be one cone, one cylinder, and a third cone. Okay, so it depends on the configuration layout of the aircraft. Any questions? Okay. So that's for the weights. So the first 4 weights now I can calculate them easy. Remember, I know all the dimensions, so I know all the areas. So let's see what are the values. Here is the exposed surface area of the wing, the exposed surface area of the horizontal tail, the vertical tail, and that's for the fuselage. So I can actually calculate the weight of each one of them. Weights multiplied by 2.5, by 2, by 1.4. So I have these 4 weights. Right away, 1 minute, and I have an estimate weight of the aircraft, of these component of the aircraft. But then comes some tricky parts. The landing gear weight is about 5.7% of the total weight. The installed engine is 1.4 times the engine weight. All else empty is 0.1%. What do we mean by all else empty? All the smaller items that we didn't mention here. For example, the hydraulic system, the air conditioning, the panels, the controls, all these small things. They are estimated as like 10% of the total weight. So let's do them. The engine, we know the engine weight. We have selected the engine, but it says here multiplied by 1.4 because the engine needs supports, needs gearbox, needs oil. So we need to add it a little bit for that. So for the engine, 1.4 times the engine weight from the manufacturer, that's the total weight of the engine. But for the landing gear and the all else empty, they depend on the total weight of the aircraft. But remember, I am doing this in order to add them and get the total weight of the aircraft. So I have a dilemma here. How do I calculate the landing gear weight and the all else empty if I haven't calculated the total weight of the aircraft? And the answer is, let's use our previous estimate. We had an estimate of the total weight before, 5,100 or 200. So the landing gear weight will be based on the initial estimate of the weight. 5% of the total weight of the aircraft is for the landing gear. 10% of the total weight of the aircraft is for all the smaller components. If I add everything in here, it will give me the empty weight that corresponds to this initial guess that I have. Is this clear up to this point? So we have calculated the empty weight of the aircraft based on the dimensions. These are new things that we had, and based on the initial estimate of the total weight. I'll stop to see if you have a question before we proceed. Okay, then what? The initial total weight was 5,000. The empty weight, we found that it's 2,000. Now I need to check, will this empty weight give me the 5,000 or not? Let's see. The empty weight, I have to add to it the payload, which is 970. I have to add to it the crew weight, which is 170. The pilot, we already know that. All these we had before. You already submitted this in your progress report. Okay. And it had the fuel weight that we had from before, 820. When I add these numbers together, the new empty weight, the fuel, the payload, the crew, I come 4,400. Now, that's not the same as the 5,000. So, the better estimate of the weight up to this point is that the weight went down from 5,100 to 4,400. That's considerable decrease. But that's not the final answer, because this new weight that I have here, if I put it in the landing gear and I put it in the all else empty, it will change these values, changing WE, and it will change again the weight. So we will do that. So based on the new weight, I will calculate three things. I will calculate the landing gear weight, I will calculate the empty weight, and I will calculate the fuel weight, because the fuel is, we have 0.159 times the total weight. This is the fuel to weight ratio that we had before. So I will take these three new numbers and I'm gonna put them in here and in here, and I will see what is the new total weight. Becomes 4,200. So you see the cycle. New empty, reduced empty will bring the landing gear and everything else down. It will bring the fuel weight down, and these three components will bring the total weight even down. So it's a sort of an iteration. We are iterating in this equation, continuously changing these two values. Let's look at the numbers. So the empty weight of 2,474, that's what we got from here. The empty weight in here resulted with a fuel weight of 820, give me a total weight of 4,000. This reduced weight brought the empty weight down because of the landing gear and all else, brought the fuel down, and this gives me 4,200. I will take the 4,200, it will change again. So things will go like this in an iteration until the numbers settle, and they settled on 4,100. They didn't change afterwards. Sometimes they settle in 2 lines, sometimes in 3, sometimes in 4. Now, is this a whole lot of work? No. It's in the same Excel sheet or your notebook or your MATLAB code. What I will do in here, I will continuously change this number, which is the total weight, this number, which is the total weight, and this number, which is the total weight. When I get a total weight of 1,000, I will put the 1,000 in these 3 locations. When the 1,000 becomes 900, I will put it in these 3 locations. When the 900 becomes 800, I will put it in these 3 locations until I get a total weight that does not change. And that would be the better weight estimate. That's the end of step number 5. Better estimate of the weight. We found that the weight is not 5,100, rather it's 4,100. This is about 20% lower weight than we had before. And with this 4,100, here are the final values of the fuel, 652 pounds, and the final values of the empty weight, 2,300 pounds. So I will stop here to see if this was clear and if you have any questions in the weight estimate.
دكتور I understand البروسيجر كله لكن مش مقنع شوي لأنه we are adding the weight of the landing gear every time, صح؟
No, we are replacing the weight of the landing gear every time.
إيه بس
Let's see.
The previous weight.
Let me go there. No, not to the previous weight. No. Do you see the weight buildup that I have on the screen now?
Yes.
When I add all of these, it's 2,474. Do you agree?
Yes.
Okay. We are going to have another one like this. These numbers are the same, but instead of the 5,000 here, I will put here 4,400 and here 4,400. So these two numbers will change. Do you agree that they will go down?
Yes.
So when I add everything again, I'm not adding them twice. I just replacing this 294 by maybe, by what? Let's see, by 252. I will replace this by 252 and I will replace this by 443. Now when you add, you will not get 2,474. What you will get is you will get 2,360. So the empty weight will change. The empty weight that will change. So it's not like we are adding the landing gear every time. So instead of the empty weight of 2,400, now it becomes 2,360. And this empty weight that has changed, when you put it here, will give you a different W naught. Yes, it will give me a different W naught. It's going to be 4,200 and so on. And this 4,200, I am going to take it and I am going to put it here. I will replace the 250 that was in here with an even smaller number. So the total will go down. Is it clear now?
Yes, yes.
Okay.
It should
So
be less than the one.
Three numbers will be replaced. Three numbers will be replaced. The landing gear, all else, and WF. WF. This also will go down because it's a percentage of the total weight. So these three numbers change from one line to the other. From this line to this line, three numbers have changed. Two in here, the landing gear and all else, and one in here, the WF. And the total, of course, will change until things settle. Any other questions? Okay. So this is the end of step number 5. We have finalized the weights. Initially, based on the range, we said we need an aircraft that weighs 5,150. Now we found out after we satisfied all the requirements, put the engine, calculated estimated weights, that we only need 4,100. Okay. So what effect do you think this has on the design? This reduced weight. What does it mean for the design? Let's look at the performance point of view, because the next step after the weight is check the performance. What do you think? What do you think will happen to all these performance characteristics that we had before? I need you to write them down. I need you, each one of you, to put on the chat box one requirement from this requirement and tell me whether it will go up or down, because simply the weight went down. And let's discuss them. What you will be doing is actually or simplified way of the performance analysis, which is the step number 6. Because after we are done with the weights, we need to check the performance. Does the design meet or exceed the requirement? So you will answer this question before we do the calculations. We will do the calculations, but your intuition should guide you on these requirements. What do you think will happen? I need a few things, actually I need many things in the chat box. Stalling speed will go down. Yes, stalling. Why the stalling speed will go down, Mohammed Musbahi? Why will the stalling speed go down? Why do you think it will go down with a lighter aircraft? Yes, because W over S will go down. Stalling speed has W over S. The weight reduced, stalling speed will go down. Good. What else? You have all the requirements in front of you, so tell me how they are going to change. Well, the requirement don't change. I mean the performance of the aircraft. How will it change?
I think it will require less power.
Is it in the requirements? The power, is it in the requirements?
But we calculated the thrust weight ratio, I think.
Yes, we calculate the thrust weight ratio, but when we check the performance, you check the requirements of the client. Yes, you have jumped you jumped maybe 10 minutes from where I want to. We will be there exactly at this point, but I want you to understand why we are going to do this. Okay, so what Sultan says, he said, let's use a smaller engine. Yes, I would use a smaller engine, but I have to ensure that I already satisfy the performance. So I will check the performance and make sure that I satisfied it. And if I don't need that extra power, I will use a smaller engine. My question now is still before that. in the performance, do you think we satisfy them all or some will not be satisfied? Okay. So with a lighter weight, the landing distance will decrease. Yes, that's a good thing. We satisfy the requirement even more than the requirement. What about the takeoff distance? It will go down. What about the rate of climb? It will go up. The aircraft is lighter. What about the ceiling? The aircraft will go higher. It is lighter. So a lighter aircraft will almost sure be guaranteed to satisfy all the requirements. More than satisfy the requirements. What about the maximum speed? It will go faster. Okay, so that's what we do in the next step. Yes. But if you barely want to satisfy the requirement, yes, Sultan is right, we should use a smaller engine. But in order to determine how small the engine is, I need to know how far did I satisfy the requirement? By what extra margin did I satisfy it? And that's what we have here in the last step, step number 6, check the performance. So what you see, what is that? In the performance here, we will go and recalculate what we had. If you have an Excel sheet, that means we are gonna put different number in the Excel sheet. We are gonna, instead of W over S that you calculated before, we will even put the new W over S because the weight went down. Or you had a cell that had W in it, we will just replace W. That's it. If you have a notebook, the same goes, just copy the equation and then we recalculate it. But if you did your work so far by hand calc, I'm sorry for you because you are going to repeat the whole thing again. And I consistently warned you not to do things by hand and calculator because we are not going to do it once. We're going to do it more than once. So the new wing loading, because of the new weight, the new power loading, the aerodynamics numbers will not change. These are CD0, K, CLmax. They have nothing to do with the weight. So these are still the same. Now, these numbers are the inputs we need into the performance equations. These are the inputs that we need to calculate the takeoff distance, the landing distance, the rate of climb, the maximum speed. I'm going to show the slides here without a comment because these are the same slides we had before, with just different numbers for the W over S and W over P. Okay, let me just jump a little bit for the equations and then I will come back to the figures. The stalling speed, that's the equation for the stalling speed. I will just replace W over S. Remember, we used this equation before in order to estimate W over S. Now it's the other way around. Now I have W over S. I will put it and I will get the stall speed. That will be the correct stall speed, and it turns out to be 62.4 miles per hour. This is lower than the 70 required, which is good. Lower stall speed is always good, because that means extra safety for the aircraft. It can slow down without falling from the sky. Okay. The landing distance. Remember, we calculated the landing distance before, but when we calculated, the unknown was W over S. Now we know W over S. So in this case, we will put our wing loading and we will calculate the landing distance. Turns out to be the landing distance 1751. That's better than the 2000 that was required. So our earlier W over S was based on a landing distance of 2000, but when we now calculating the wing loading, we found that the landing distance is 1750. The same for the takeoff distance. So these are exactly the same thing, but in the takeoff distance, the unknown was the thrust to weight ratio. But now I have the thrust to weight ratio or the power to weight ratio. So the unknown is the takeoff distance. And it's again 761. It's better than we had before. So for landing and takeoff and stall, things are better. What about the other requirements? What about the range? If you look at the range equation, it doesn't have the total weight of the aircraft. So it's not sensitive to the changes we did to the weight. Because in the range equation, we have weight ratios, WF over W, and this did not change. The WF over W was, what is that one? 0.159. This one did not change. It's the same. So the aircraft will have the same range, 1200 feet 1200 miles with the same fuel tank. It will go with with the same engine. It will go for 1200 miles. Range did not change. We satisfy the range, but not over satisfy the range. The rate of climb, we have an equation for the rate of climb. If you substitute with the new thrust, with the new weight in the rate of climb, you will find that the rate of climb at sea level, what was the required rate of climb? Can you remind me? At sea level, the rate of climb was what? Your project, what is the rate of climb? يا شباب.
دقيقة بس لازم نفتح
لا مش لازم تفتح. It should be on the top of your mind. You have worked on it. 1000 feet per minute. The requirement said the rate of climb was 1000 feet per minute. That was the requirement. Okay. And now when we calculate the rate of climb, we find no, it's not 1000, it's 1580. Okay, because this x-axis here is in hundreds of feet per minute. So it's 1500. That's almost 50%, more than 50% extra rate of climb, which is good. And by the way, in the rate of climb, you have the density, right? So if the density changes, if you change the density, you will find the rate of climb will decrease as you go up. But the requirement was at sea level, that it should be 1000 feet per minute at sea. We didn't have a requirement here. We just draw this for our own information, but the requirement is just this point. Okay, so you will find that you satisfy this requirement. What about the maximum speed? If you look at the equation of the maximum speed, it has the horsepower to weight ratio and it has the weight. And if you substitute there, you will find that the maximum speed now becomes 400 something, maybe 430 or 420. The requirement said that we needed 250. That means there is a huge increase in the Vmax in here. I'm just substituting in the equation. Now, if you want to see this graphically, what does that mean? That means if we maintain the same engine, that's the available horsepower. What happened is when the weight went down, the lift went down. And when the lift went down, the drag went down. And that means the total drag, which comes from the drag polar, went down. That means the required horsepower went down. So instead of the curve being here and intersecting at 250, the whole curve went down. And now the intersection is at 420. You see that? What I'm doing now, I'm describing by words the equations. The total drag comes from two terms. Dynamic pressure times area times CD naught. And the other term comes from the CL. And the CL went down because the weight went down. Right? So the total drag went down. And if I multiply this by the power, by the speed, that will give me the power. So the power went down. And when the power went down, now it intersects here at a higher value. Intersects in the equation means the power is equal to the power of the engine. And this happened at 400 something. Go back to the equation of where we calculated the maximum speed and you will find that the maximum speed went up. So all the aspects of the design went up. All were improved, maybe only the range is still the same. Okay. So what does that mean to our design? That means that the design is better than the requirements. Now, you do this and you can be happy and you can get fired from the company. Because if you make a design that's better than the requirements, that means the design is going to be more expensive than the requirements. Why? Because I can, if I am your competitor, I'm another company, I can satisfy the requirements with a smaller engine, as Sultan suggested, smaller aircraft, cheaper aircraft, and I will satisfy the requirements. So I will sell my product and you will not sell your better product. So your company will be bankrupt. So your company would better fire you now before you do this. See the point? So if the design over satisfies the requirements, in this case, in our case here, because the engine is too big, so we call that design a hot design because it's hot means offer power. Then that's not the best design because it's going to be more expensive than other competitors. And we need to optimize the design. Is this idea clear? Because it's very important. If you over satisfy the requirements, well, you can't tell your client you over satisfy them, but you must tell him in order to only satisfy the requirements, this is what you need. So I will stop before we discuss the optimization to see if you have a question up to this point. Okay. So optimization will mean that we make a design decision. Where does this fit in our great plan? Well, in the plan, this is where we do that. It is here. We check the performance, we check the takeoff distance, landing, everything. Everything is more than satisfied, but yet I have to iterate. And this iteration here by making a decision. The decision here is to use a smaller engine rather than the 360. I don't remember the number. We should use a smaller engine. If I use a smaller engine, now I need to recalculate everything. The new wing loading, check the performance, draw the configuration. So probably the wing is going to be smaller. Probably, maybe the fuselage cabin will not change much. The tail cone will not change much, but maybe the nose part will be smaller because the engine is smaller. I will need a smaller engine. And when I check the weight again, it will be lighter because the weight of the engine is smaller and the landing gear is smaller and so on. I will check the performance again. Are they satisfied or did I miss the whole thing? Maybe one final iteration and I will have the final design. I can put final touches afterwards. Now this cycle is not a part of AE240. We will not do that. It's not even done in the textbook in chapter 8. It just mentioned that after the final step, which is the performance, we need to make a decision of reducing the engine size. That will reduce the fuel tank, the wings, the weight, and iteration should be done until we get the final design. In AE427, we do one other cycle because we start earlier in the semester. We start from week 2 working on the project. Okay. For you in the final report on Wednesday, all you have to mention is after you check the performance, you have to come up with a decision. Maybe not all of them are satisfied. Maybe some are satisfied and some are not. Then the comment will be, for example, maybe to increase the wing area a little bit to ensure that the landing distance is satisfied if it's not satisfied. Okay, so the decision will depend on the outcome of the performance analysis. After we look at the performance, you come with your decision, but do not implement the decision. Just mention it, and that will be the end of your work. Okay. Now, again, this might seem like a lot of calculation. No, actually, if you have them, if you have the equations in Excel, notebook, or MATLAB, you will just put different numbers and you will get the same answer. Oh, so, I mean the final answer, but you will just using a different number. So that's the scope of the work that we have. In 427, inshallah, you are going to do more than this because we have been, or the textbook here has been reducing things to fit sophomore level course, but there is more to say in every aspect, in the estimation of CD0, in the estimation of K, the performance, everything. But here you have seen one full design cycle. I would say maybe the only missing part is the cost. You don't know how much this aircraft will cost. Again, in A427, we have a model to estimate the cost at this level of the design. So let's see if you have any questions. Yes, I mean.
Yes, Doctor. How can companies compete if this is the case? I mean, they will both try to minimize and they will try to do multiple iteration until they get to the minimum price. They will be the same.
A very good question. How do car companies do that? How do you go and buy your car? You have set of requirements, right, in your mind. You want it stylish, you want it certain power, maybe certain number of passengers. I need it 4 or 7, right? You have something roomy. Cost is an issue, right? The thing is, if all clients have the same requirements, we will have one car and one airplane. But we have different clients and different requirements. So it's up to the company to find a niche for their product. What exactly is missing in the market right now that would make it compete? For example, 20 years ago, there were no Tesla cars, right? Tesla cars, the electric cars, there were none. Right? Everyone was buying cars, but they came at a point where they figured out that the technology has emerged. They can allow electric cars. There is a need for better environmental friendly cars. No one has done that, and their market survey indicate that there are some needs. So maybe if we can satisfy that, we will get that design. No one was optimizing from that perspective at that time, maybe only Toyota. Okay, so the same comes with the aircraft. Not the companies will compete because we have different requirements and they can satisfy them at different levels. For example, you have 5 teams in your section, in your design project. You will probably come with 5 different designs. Because if we started with a different configuration from the beginning, different concept, then everything will change. And I might end up having 2 aircraft, both satisfying the requirement, the basic requirement that I gave to you, but some is better, one of them is better in a different aspect. Okay, and if that aspect is important to some client, this aircraft will sell. If not, they will not. And that's why you have some aircraft design projects that are being dumped. They are just being dumped, and we said that at the beginning of chapter 8 or chapter 7. They found out that after a while, no, there is the other competitors satisfy them either better, or there is no market for the good thing that I have in my design. Does this answer your question?
Yes, thank you.
So it's different aspect. It's not only the set of requirements that we have at the very beginning, it's what's the end product. When you start to talk about product design, it's not just engineering design. There are many issues. How the aircraft appeals. What's the cost of operation? You see, when we optimize it, did we mention anything about how much this aircraft is going to cost per year? No. Because now you have to go into the design of the subsystems, the maintenance, how much the centers go. So the design is not complete up to this level. The conceptual design is complete, but the aircraft has to go through preliminary design, detailed design, and that's in the details where the devil is. So this is another issue for which aircraft can compete. Okay. Any other questions?
ايه دكتور بس تسمح نراجع قيمنا معك؟
Do what?
القيم.
Okay, I will talk to you, but any other questions in the topic, and then we can, so that if they can leave, if they have any other classes? I already had attendance. So guys, we are done here. If you want to leave, you can leave. If you want to stay with us, I can check some values for some teams. And feel free to bring any questions for your design projects from now until Monday, because if I were you, I wouldn't do any work after Monday. I will just focus on writing the final report. Okay, because it's very good. It's very important to present your work in a good way, rather than continue the work up to the last minute. Okay, so I'm ready if you want to show me some numbers.
كيف يا دكتور ارسلها لك على الواتس ولا؟
زي ما انتوا عايزين. If you want to share it here now, I can look at it now. If you want to send it on WhatsApp, but send me the Excel sheets, add me to the group, whatever. It's up to you.
طيب.
Okay. Okay, شباب. Any other questions? Okay, thank you. So I'll see you